Now, an important goal is to show that these integrals now, where f is analytic and gamma is a continuous curve, we want to show that it's invariant under deformations of the curve gamma. And the precise term for deformations is homotopy, so we need to review what homotopies are or learn them for the first time. So two curves, gamma naught and gamma 1, which we'll parameterize using the same interval, which have the same starting points and the same endpoints, are homotopic in the domain U inside the complex plane if they're deformations of each other in the sense that there exists a continuous function phi, which is defined on the interval 0, 1 across the interval a to b, such that, let's see, when I plug in 0 for the first value, I just get back gamma 0, and when I put in 1, I get gamma 1. But then in between, you might label the curves gamma sub s of t, and we want phi to kind of be this continuous function that takes you from gamma 0 to gamma 1 in a continuous fashion. We also want all of these curves as you go to have the same endpoints the whole time and the same starting points. So we also require that for every s, that phi of SA is the same as gamma naught of A, and phi of SB is the same as gamma naught of B. And kind of the picture of a homotopy is just, well, here I have a domain U, and I've drawn this blue curve. And so this curve right next to it will be homotopic to it. But this red curve here will not be homotopic to it because I put this part here that's not in the domain of U. And so to attempt to kind of deform the blue curve to get the red one, you'd have to pass through this area that's not in the domain, and you can't do it. Okay, we also need to talk about homotopy of loops, and that's pretty similar. So recall you have a loop when it starts and ends at the same point. Okay, so two loops, gamma naught and gamma 1. So there'll be loops, but their starting points don't have to have any relationship to each other. They'll be homotopic in U, and we'll just say loop homotopy if we need to be specific. If something similar happens, there exists a phi that takes you from gamma naught to gamma 1 in a continuous fashion with a bunch of loops. So the way we write it is that we start out at gamma naught, and then we get to gamma 1 at the end. And then we want to make sure everywhere in between we have loops, so we have that the value at A and the value at B for all S is the same. So this is just the requirement that all of these intermediate curves are loops. And we also say that a loop is null homotopic in U if it is homotopic in U to a constant curve. So this would be the situation where I have a loop that I can shrink to a point. But here's a picture of some homotopic loops. But being homotopic in a domain very much depends on the domain. You can't have the definition that sort of that leaves out the domain. It's essential for it. Okay, and then this lets us precisely state this really important theorem. So let U be a domain and let F be analytic if gamma naught and gamma 1 are homotopic curves, or if they're homotopic loops in the sense of loop homotopy inside of U, then these integrals are the same. So they don't change under this deformation. And if gamma is null homotopic, so you can deform it to a point, then integral of f over gamma is 0. And the proof of this is a little technical, so we'll do it later, but now it's good to just go through a bunch of applications.